Hello, and welcome to the next video in my series on basic statistics. And for this video, finite mathematics. The concepts we're going to talk about in this video can apply to both disciplines. So you may be watching this video in the context of a stats playlist or a stats class, or a finite playlist. Either way, it applies to both. Now just a reminder, these videos are geared towards individuals who are relatively new to stats or finite math, so I will just be going over the basics. And finally, if you're watching this video because you're struggling in a course, keep your head up. With a little bit of help, we can get you on the right track, and hopefully these videos will help. So stay positive. With all that being said, let's go ahead and get started. Now in this video, we're going to cover the basics of permutations and combinations. Now I've worked with dozens and dozens of students in finite math and stats that still have a hard time teasing apart these two ideas, because in some ways they're not intuitive to how we think about counting things. So hopefully with some examples, we're going to tease these two apart so you can really understand the basics of how each applies to whatever problem you may be working on. Now let's talk about the importance of counting in general. Now counting sounds very simple, right? I mean, we begin counting at a very, very young age. So at this stage, I have a 3-year-old nephew that's just beginning to count, past 10 and things like that. So counting comes natural to us at a very young age. But in statistics and finite math, counting assumes a very important and complex role, because the probability of an event or an outcome is central to a large portion of statistics and finite mathematics. Because probability by definition is the frequency or the count at which some event happens out of a greater number of outcomes. So to figure out probabilities, you have to be able to count in more complex ways than we're used to. And these problems can get very confusing and very complex, even though underneath the sheer counting of them are not. So we often deal with events that have numerous outcomes or a combination of outcomes, and we have to be able to have the tools to count those things so we can find certain probabilities. And that's why it's important in stats and finite math. So first, let's talk about what a permutation is. Now here's the formal definition. It's the number of different ways that a certain number of objects can be arranged in order from a larger number of objects. And I highlighted there, arranged in order, because that's important. So in a more abstract definition, if there are n number of objects, like total number of objects, how many different ways can we make ordered lists of a certain size? So in this case of size r. So we have a total number of objects that's n, that's sort of the abstract way of thinking of it, and we're interested in how many different ways we can make ordered lists that are of size r long. And we're going to talk about some examples in this video. So if you want a more concrete example, it's coming right up. Now how do we write that? There are actually several ways this is written in statistics and finite math, but I'm going to stick to the one I know and use in finite math courses. So in this case, we have capital P, which means permutations, and then in the parentheses we have n, comma, r. So of course the n means the total number of objects or events that we're looking at, and then r is the subset of how many different, in this case, how many different ordered lists can we make. In combinations, it'll be a little bit different. But this is the actual way it's written. Now you might see it with a P with an N on the top and an R below it. It just means the same thing. But this is how I use it, so I'm going to go ahead and write it this way. Now let's talk about combinations. And of course, these two concepts are close cousins. They are related closely. So here's the formal definition. It's the number of different ways that a certain number of objects as a group can be selected from a larger number of objects. So the important thing here is as a group. We often say this as N choose R. So again, the number of total objects, and we're choosing R of them. So if there are N number of objects, total number of objects, how many different ways can we select groups or sets of size R? So think about the difference between permutations and combinations. In the permutations, it's about an ordered list. So each individual item has its own sort of order or place. In combinations, we're talking about sort of a group or a set, or with my students, I call it a clump or a blob, because it's just a collection of whatever we're looking at. And again, we'll look at examples here in a minute. And this is how it's written. So C, and in parentheses, N, comma, R. So this would be N choose R. So N is the total number of objects or events we're looking at, and then R is the size of the groups we want to look at. So here's how we can visualize the difference. So we have permutations on the left and combinations on the right. In a permutation, we have each individual item in an ordered list. So the order matters. So the fact that the red smiley face comes first matters, the fact that the blue one comes second matters, and the fact that the green one comes third matters. So think about it. If we were putting these in some order, how many choices will we have to put in slot 1? Well, we could have 3. We could put any one of the 3 in that first slot. Now, move on to the second slot. Now how many choices do we have? Well, we already put one of the smiley faces in the first slot, so we only have 2 left. So for the second slot, we have 2 choices. So we fill that, and then we go to the third one. Now how many choices do we have? Well, we only have 1 left. So in the first slot in our order, we had 3 choices. In the second slot, we had 2 choices. And in the third slot, we had 1 choice. Now, look at that compared to a combination. We just have 3 smiley faces in a bucket. That's it. It's a group. You got to think of them as a group. So on the left, we think of things in individual order. On the right, we think of them just as a group. So if we have 3 things, 3 smiley faces, how many groups of 3 can we have? Well, there's only one way. So we have 3 things. There's only one way to have a group of all 3 of them, and that's all 3 of them. So that's 1. Okay? So on the left, we have ordered list. And on the right, we have an unordered group or set. So think of the permutation as an ordered list, and the combination, the 3 smiley faces in the bucket, is just a collection or a set or a blob or a clump of things. The order of the smiley faces in the bucket doesn't matter. So here's a horse race example. Let's say you have a horse race that will include 10 horses. You were given 2 betting options. You can choose the top 3 horses regardless of finishing order, or you can choose the top 3 horses in exact order of finish. How many possibilities are there for each outcome? So think about this. In the first case, we're just sort of choosing or betting on the top 3 horses. They can finish in any order. So if there are 3 horses that are named red, blue, and green, if the race finishes red, blue, green, or green, blue, red, or red, green, blue, it doesn't matter, as long as those 3 horses finish in the top 3 spots. But in the second scenario, they have to finish in the exact order we choose. So if we place a bet at the window, and I've never done this, you say, I'm betting that they will finish in red, green, blue. Well, you only win that bet if they finish red, green, blue. But in the first case, if they finish red, green, blue, you win, because the order does not matter. And that's a really simple way of thinking about permutations versus combinations. So if with the top 3 in any order, we have 10 choose 3. So there are 10 horses, and we're just going to choose 3 as a group. So how many groups of 3 horses, 3 different horses, can we have out of 10? Well, the answer is 120, and we'll talk about how to calculate that in this video and in the next video. So there are 120 different groups or clumps or sets of 3 horses that you can make out of 10 total horses. Now what about the top 3 in exact order? And that's a permutation, 10, 3. Well, in that case, there are 720 possibilities, because order matters. So there are going to be more outcomes that fit that criteria. And this should make sort of common sense at this point, because remember how I said it. If the horses are named red, green, blue, in the first scenario they can finish in any order, and that counts. So there are fewer possibilities. But in the second example, because they have to finish in exact order, there are many more possibilities of that happening, because of the exact nature that's required to meet that criteria. Now, of course, which option do you think will have the higher payout if you are correct? Well, the second example is less likely to happen. There are 720 possibilities, and you have to be exactly right on one of them. In the first example, there are only 120 possibilities, and you have to be right on one of them. So you can see the odds are much greater for being correct in the second example. In the first example, it's a little bit easier to make your bet. So here's a baseball example. During most of the season, a Major League Baseball team has 25 active players on its roster. Now, if we ignore playing positions in the field, we're just going to ignore that there's a pitcher, catcher, and stuff, okay? So ignoring playing positions. A manager must select 9 players for each game. So, how many unique groups or sets of 9 players out of the 25 could be a potential lineup? So think of a bucket full of 9 players. We don't care what order they're in, we don't care anything. Just a bucket of 9 players, and how many buckets would we have that have a different set of players in it? So this is 25, choose 9. That comes out to 2,042,975. That's pretty astonishing, isn't it? Most people wouldn't think that number would be that high. But if you have 25 total players, you can make over 2 million unique groups of 9 players out of that 25. So you can see why it's important to begin to understand how to count things that are less intuitive and have much higher numbers. Now, this is not a lineup. We're not putting them actually in order like a batting order, but we are now. Now, how many lineups? An ordered list. A lineup is an ordered list. You bat in an order. Could the manager make using 9 of the players out of 25? So hence the batting order. Now, order matters. Now, before I click the next little button here, I want you to think about this. Up above, if I have a group of 9 players, that counts as one of my groups up there. But for that one group of 9 players, think about how many different orders I could have for that one group of 9 players. For the first slot in the order, I'd have 9 choices. For the second slot in the order, I have 8. For the third slot, I would have 7. All the way down the batting order. So you can see why permutations are much more numerous than combinations when dealing with problems like this. For every combination above, there are many ordered lists that can be made out of one combination from the above question. So this, believe it or not, 25, 9, the permutation, if my scientific notation is correct, I think, don't hold me to this, but I think that is about 741 billion different lineups. Yes, that is correct. So, if the team has 25 players, and you're making batting lineups of 9 players, you could have 741 billion different lineups, ordered lists. Isn't that amazing? So again, I think that's 741 billion, but if it's not, it doesn't matter. It's still a big number. So you can see how numerous the permutations are. Now this is the last example. This is investment selections. So there are 30 stocks in the Dow Jones Industrial Average, which is the one you hear on the news every day. So over the next 6 months, you decide to invest $1,000 in a different stock each month. So the first question is, how many unique groups or sets of 6 stocks are possible? So a bucket of 6 stocks out of the 30. Well, that is 30 choose 6. So in this case, there are 593,775 different buckets of 6 stocks we could choose out of the 30. It's quite a number, isn't it? Now, how many investment lists could be made? This is the order of the investments to be made over time. So next month, you have 6 choices for an investment. The month after that, you have 5 choices for an investment. And the month after that, you have 4. This is like an ordered list of your investments over the next 6 months. So that's 30, 6. That's a permutation. Now look at that number. That is massive. That is 427,518,000 different ordered lists of 6 stocks out of 30. It's just tremendous. But that's what it is. So, like above, if we pick 6 stocks in our choice and our combination section, for that one choice, that one bucket of 6 stocks, if we then go arrange that bucket of stocks, we'd have 6 choices for the first month, 5 for the second month, 4 for the third month, etc. So we have to do that 6, 5, 4, 3, 2, 1 for every combination above. And that's why that number is massive. Okay, let's just review and then we're done. So a permutation is an ordered list. So in our smiley face example, in the first slot we had 3 choices, in the second slot we had 2 choices, in the third slot we had 1 choice. So in this case, we'd have 3 times 2 times 1, which is 6 different ordered lists. And actually, if you sat here for a second, you could probably figure them all out in your head. Let's say we start with red. We could go red, blue, green, or red, green, blue. Now let's say we start out with blue. We could go blue, red, green, or blue, green, red. Or if we start out with green, we could go green, blue, red, or green, red, blue. And those are our 6 permutations for those smiley faces. However, in our combination, it's just 3 choose 3. We have 3 total things. How many ways can we reach in the bucket and pull out 3? There's only 1. And I actually want you to think about the physical act of doing that. If I have 3 tennis balls or whatever it is in a bucket, and I say, okay, reach in there and pull out 3. Well, how many ways can you do that? There's only one way to do that. If there are 3 in there, and I say reach in and pull out 3, you're going to grab all 3. There's only one way to do that. But you can see there are 6 ways to arrange them in order over here on the left. So, ordered list, an unordered group, or set, or blob, or whatever. No order on the right, but order on the left. Okay, and that covers our basic video on permutations and combinations. Now in the next 2 or 3 or 4 videos, I'm not quite sure yet, I'm actually going to go into very specific examples of each concept. So we'll do a video or 2 on permutations with some problems and examples. We'll do a couple of videos maybe on combinations that have problems and examples. So you can actually see how these things work in actual problems you're likely to come across in your stats class or your finite math class. Alright, so that wraps this up. Just keep in mind, if you're having trouble with this in your class, keep your head up, stay positive. With the right amount of work, we can get you through that. If you have any comments or questions, please leave those below this video. If you have any suggestions on how I can make the videos better, also leave those down below, as long as they're constructive. I don't mind constructive comments. Okay, let's go ahead and wrap this up. Again, thank you very much for watching, and I look forward to seeing you again next time.